Dear students, in this video we are going to see some practice problems in memory management. Finding how many address bits are required. Consider a logical address space of 32 pages with 1024 words per page mapped onto a physical memory of 16 frames. How many bits are required in the logical address? How many bits are required in the physical address? First, let us consider how many bits are required for the logical address. Here the memory is each page. Here the page size is 1024 words and there are 32 pages are there. To represent a page of 32 pages, we required 32 pages means 2 power 5 pages. 5 bits are required to refer the page number. 1024 words means 2 power 10 words. So to represent the address we require 10 bits. So therefore the total number of bits for referencing an address in the logical address space is 15 bits. 2 power 5 represents 32 pages. 2 power 10 represents 1024 words in each page. So totally put together we require 15 bits. That is the number of bits required for representing an address in the logical address space. Coming to the physical address space, here there are 16 frames are there and each frame is of size 1024 words. Because in virtual memory the pages and frames will be of same size. When page is of 1024 words means frame is also 1024 words only. So therefore for representing 1024 words we require 10 bits. For representing 16 frames, 16 means 2 power 4. So 4 bits are required. Put together 14 bits are required for referencing an address in the physical address space. Let us see another example of the same case. Consider a logical address space of 64 pages of 1024 words each mapped onto a physical memory of 32 frames. Finding effective access time. Consider a paging system with page tables stored in memory. If a memory reference takes 200 nanoseconds, how long does a page memory reference take? In this problem, the time taken for memory access is 200 nanoseconds. And we assume that consider a paging system with page table stored in memory. The memory access time is 200 nanoseconds and how long does a page memory reference takes? 400 nanoseconds, because 200 nanoseconds to access the page table and 200 nanoseconds to access the word in the memory. So totally 400 nanoseconds are required for accessing a page in the memory. Next, coming to the second problem, if you add the associative register and 75% of all page table references are found in the associative register, and what is the effective access time for this case? If 75% of the address pages are in the associative register, the effective access time for this problem is computed as P into TLB hit time plus 1 minus P into TLB miss time. So where TLB hit time is equal to TLB search time plus memory access time. TLB miss time is equal to TLB search time plus memory access time plus memory access time. Because if you don't find the page in the TLB, then we have to search the page table and find the frame number for that particular page, so which requires a memory access time, and after finding the frame number we should access the corresponding location in the page physical memory, so that requires another memory access time. So totally we require 2 times for memory access time. The effective access time is calculated as P into TLB hit time plus 1 minus P into TLB miss time. Here in this problem we have given 75% of all page table references are found in the associative register. That means 75% of the time we have TLB hit. Remaining 25% of the time we have TLB miss. So we substitute that values in the effective access time calculation. So 75% means 0.75 multiplied by 200 nanoseconds plus 0.25 into 400 nanoseconds, because here in this problem they have mentioned that the time taken for TLB search time is 0. So therefore 0 plus 200 into 200, that is 400. So 0.25 into 400 nanoseconds. Total the effective access time will become 250 nanoseconds. Let us take up another example. Memory access time requires 200 nanoseconds. Then average page fault service time. That means if there is a page fault, we require milliseconds of time. So what is the effective access time in this case? So that is 1 minus P into TLB hit time plus P into TLB miss time. So here one access out of 1000 causes page faults. That means 1 by 1000 is the page fault, that is TLB miss time. So remaining time it is hit. So therefore when it is a miss, 1 minus 0.001, we have to spend 200 nanoseconds of time to access the page from the physical memory. And the remaining time when it is hit, we have to spend only 8 milliseconds for accessing the content of the physical memory. So the total time taken for the effective memory access is 8.2 microseconds. Finding the physical address. Consider the following segmentation table. There are 5 segments. Segment 0, 1, 2, 3 and 4. The segment 0, the base register content is 219 and the length of the segment is 600. Segment 1 is located from the address 2300 and its length is 14. Segment 2 is located from 90 and its length is 100. Segment 3 is starting from 1327 and its length is 580. Segment 4 is starting from the 1952 location and its length of the segment is 96. What are the physical addresses for the following logical addresses? So here you see that 0, 430. 0 is nothing but segment number and 430 is nothing but the offset within the segment. So we need to refer the instruction number 430 within the segment 0. That is the meaning of this 0, 430. So segment 0 is starting from 219 location. So therefore 219 is the base address. Plus we have to identify the instruction number 430. So therefore 219 plus 430, that is equal to 649 is the actual address of this particular reference 0, 430. Coming to 1, 10, the segment number 1 is starting with the 2300 and the length is 14, but the required instruction is 10. So 2300 plus 10, that is equal to 2310. That is the address of the reference 1, 10. Coming to the next reference 2, 500. Segment number 2, but the instruction reference is 500. But segment 2 is starting from 90. Okay, 90. But the length of the segment is only 100. 100 instructions are there in the segment number 2. But here the instruction reference is 500. That much size is not available for the segment number 2. It leads to illegal memory reference. So it generates a trap to the operating system. So therefore this is an error. So this address is not available in the segment. It is a illegal reference. So operating system gets a trap when this reference is made. Then coming to 3,400. Segment number 3 is located from the base address 1327 and the instruction number 400. So 1327 plus 400 is equal to 1727 is the address of this particular reference. Next, coming to 4,112. Segment number 4, the size is 96 only, but the reference is given 112. So it is a illegal reference. Therefore, operating system will get a trap. So therefore, illegal reference is not permitted. So that this generates a trap to the operating system. This is how we find the address for the given reference in the segmentation. Thank you for watching this video.